Good afternoon. We are going to cover the mole concept in this video. By the time you are finished, you should be able to obtain, evaluate, and communicate information about how the law of conservation of matter is used to determine chemical composition in compounds and chemical reactions. You should be able to use mathematics and computational thinking to apply concepts of the mole and Avogadro's number to conceptualize and calculate percent composition, empirical and molecular formulas, mass, moles, and molecules relationships, and the molar volume of gases. We introduced the mole concept to you in our last lesson where we discussed the SI units and we defined it as the amount of substance. The easiest thing that I can tell you as a relationship for the mole is using a term like a dozen or a pair, something that no matter what we're talking about, it always represents the same number. So whether you go to Dunkin' Donuts this morning and you bought a dozen donuts, or like me as a golfer, I went through a dozen golf balls in my round of golf last week. Just kidding. But the same number of particles, no matter what we're talking about, whenever we describe a dozen. That's essentially what the mole is talking about. So we have the mole, it's abbreviated as MOL. Don't ask me why, I don't know. But they have MOL as its abbreviation, and 1 mole is going to be equivalent to 6.022 times 10 to the 23rd particles, and that could be atoms, molecules, ions, formula units, whatever it happens to be. In this, you can label your molecules as MCs for me. This is something that is for me only, and you can label your formula units as FU. It's the only time you can tell me FU in class and it'll be okay. So when we look at these, you could have grains, particles, there are a number of different things. If it's not really something to do with a mass like grams or liters for a volume, then you can assume that it's going to fall under that particles category. So we have 1 mole also equaling 22.4 liters for a gas at STP. Now that STP, the S stands for standard, the T is temperature, and the P is pressure. Those have specific values. Standard temperature is going to be 0 degrees Celsius or 273 on the Kelvin scale, and the pressure is going to be 1 atmosphere or any of its equivalents. 760 millimeters of mercury, 101.325 kilopascals. And finally, the last thing that the mole can be equal to is the molar mass. Now we will talk about all these in depth and go through some examples for each one. So we'll define molar mass shortly. Okay, so I want you to take a moment and pause the video and copy down this mole roadmap. This is going to be a very helpful tool for you, especially at the very beginning when you're trying to figure out how to work all these problems. So what this does is this just gives us a little concept map that kind of shows us what conversions we need to use to solve a particular problem. So all you need to do is identify what your particular units are, such as mass having grams, or the liters for the volume, and then your atoms, molecules, or formula units for your particles. So this is going to be kind of a way to tell where you need to go as far as your conversions to solve a problem. So anytime that you're going from the bubbles on the outside towards the mole, when you go in this direction, you're always going to be dividing by those numbers, either the molar mass 22.4 or the 6.02. That's going to allow you to cancel off the unit that you're starting with. When we're dealing with something going from the mole out to one of these outside places, then you're going to multiply the moles by whatever those conversions happen to be. And again, it's all based on unit cancellation. You only have 3 numbers that you have to be able to calculate or remember in order to do these problems. Okay, so we're going to go through these different mole conversions one type at a time. The first one that we're going to look at will be the number of particles. This number was determined experimentally to be 6.022 times 10 to the 23rd. However, because it is such a large number, we just round it down and say 6.02 just to make it a little bit easier. It was named in honor of Amadeo Avogadro, who first proposed in 1811 that the volume of a gas depends only on the number of atoms or molecules, not on the type. So it doesn't matter what the identity is, it just matters what the number of them is at a given temperature and pressure. So we have Avogadro's number, symbol is Na, and it's 6.02 times 10 to the 23rd. Now, just so you kind of get a sense of the scale for this, because that's something that a lot of people always have trouble visualizing. If we were to line the equator of the Earth with nothing but hydrogen atoms in a single file line going all the way around, we could wrap the hydrogen atoms around the Earth over 1,000,000 times. Also, if we were to think about the volume, if we had a mole of softballs, 6.02 times 10 to the 23rd softballs, in that situation, they would have about the same volume that the Earth has. And finally, if we were to stack a mole of pennies, 6.02 times 10 to the 23rd pennies, in a single file line, they would stretch all the way from the Earth's surface to the moon. So really, really large number of atoms, so that can kind of give you a sense of just how small those atoms are. So when we are looking at these conversion factors, we want to write a conversion factor for the number of particles two different ways. So every single problem, you're going to use one of these two conversions. I can either have 1 mole over the 6.02 times 10 to the 23rd, and I'm just going to say particles because it can be any of those that we were talking about, or it could be 6.02 times 10 to the 23rd particles over 1 mole. Which one we choose depends on what units we're starting with, because again, we want to have the units cancel, one in the numerator, one in the denominator, when we're doing our math. Okay, so let's look at a couple of example problems really quickly so you can kind of see how to do this. Notice here I'm starting with atoms of carbon as my beginning substance. So I'm going to write down my given information, and just like with dimensional analysis problems that we were doing before, the number of significant figures in our beginning number is going to be what we use for the entire answer. For your problems, you must have not only a unit, but a symbol for what substance it is. So it's not enough to just simply say atoms. We need to say atoms of carbon for our answer to be right. When you are doing your work, I want to see this for every single problem that we do. Now, I realize it gets redundant, but later on, the beginning of next semester, we're going to start doing these types of problems where we're going between different substances, and it can be very easy, especially when you get multi-step reactions, to lose your place. So by putting this down and having not only the symbol but also the unit, it can really help you stay organized in the process. So now at this point, I'm going to go ahead and make my little T-chart. It could be the parentheses if you'd prefer, but notice here I have atoms of carbon in my numerator, so I'm going to place atoms of carbon in my denominator, and I'm going to convert that into moles of carbon. So at this point, I can now place in 6.02 times 10 to the 23rd, and I can place 1 mole in the numerator. Now, when I plug that into my calculator, if we do 1.25 times 10 to the 24th divided by 6.02 times 10 to the 23rd, we should get an answer of approximately 2.08 moles of carbon. Okay. Now, for our next example, sulfur dioxide, that is SO2. I would not expect you to know that yet. So when I look at this, I would start with 2.45 moles of SO2. And now I have the moles in the numerator, so I need to have the moles of SO2 in the denominator to make them cancel, and I can do molecules of SO2. Remember, for me, you can abbreviate the molecules as MC, so you don't have to constantly write it out. So I'd have 6.02 times 10 to the 23rd molecules for 1 mole. And now I can simply multiply 2.45 times 6.02 times 10 to the 23rd, and I end up with 1.47 times 10 to the 24th molecules of SO2. Now for this last problem, we have one more little thing that we need to look at here, and this one is asking us for the number of atoms of fluorine that are present in a certain number of moles of a compound. So this one just has one little extra step that we're going to take, and so I'm going to start by having 4.80 moles silicon tetrafluoride, SiF4. So I'm going to do the same principle, same process there to start off with, and I'm going to have 1 mole of SiF4 and 6.02 times 10 to the 23rd for the number of molecules. And now for every 1 molecule of the SiF4, I have 4 atoms of fluorine. So I can now go ahead and plug those numbers in, and if we do that, we end up with 1.16 times 10 to the 25th, and then I would have atoms of fluorine. My molecules would cancel, my moles would cancel, leaving me with the atoms. The second conversion that we're going to look at involves mass. So in order to convert from mass into moles, we need to determine the molar mass of a compound, which is listed as the number of grams found in 1 mole of the substance. 1 mole, or 6.02 times 10 to the 23rd atoms or molecules, is the amount of atoms of any element that has a mass in grams equal to the mass of 1 atom in AMUs. If you recall from our last unit, we talked about AMUs, and it is a really small number for the mass in grams of a single proton or neutron. But if we multiply the number of protons and neutrons in the nucleus by the mass of the proton and the neutron, and then by the 6.02 times 10 to the 23rd atoms, it should come up with the number of grams that would be equal to the atomic mass units. So for us in the simple portion of this, all we have to do is look on our periodic table and see what the average atomic mass is, and that will be our molar mass in grams per mole. So if we look at an atom of carbon, 1 mole of carbon atoms, again 6.02 times 10 to the 23rd, would be 12.01 grams. The unit for the molar mass will be grams per mole. So if we want to write 2 conversion factors for molar mass calculations, we would have grams over 1 mole, or we would have 1 mole over grams. Now this number again is going to change because the internal guts of each element will be different, because they're going to have a different number of protons and neutrons. So when I look at a simple compound, or simple element, we want to look at our periodic table to determine the molar mass. So the first one there, if we look at for cobalt, you can just round these to the hundredths place. So we would have 58.93 grams per mole. For sulfur, depending on your periodic table, it's either listed as 32.06. The one that I gave you lists it as 32.07, and then grams per mole. Arsenic, when we look at that, we will have 74.92 for our grams per mole. And then finally, antimony will be 121.76 grams per mole. For compounds, the molar mass will be the mass in grams of 1 mole of any compound. So in order to obtain the molar mass, we need to multiply the number of atoms times their atomic mass or molar mass, and then add all the individual elements together. And once again, we're just going to round everything to the hundredths place for this. So as an example here, you can see already we have O2. That means that I have 2 atoms of oxygen, so I'm going to multiply the molar mass of oxygen, 16 grams per mole, off my periodic table, times 2. So oxygen gas would have a molar mass of 32.00 grams per mole. So now, as we look at a few more examples here, when I do my first example, NaCl, we have 22.99 plus 35.45. So that gives me a total of 58.44 grams per mole. When I look at the second example, carbon, 12.01 plus 2 times 16.00, that gives me a grand total of 44.01 grams per mole. When we come to our third example, potassium sulfate, K2SO4, I have 2 atoms of potassium, so potassium's 39.10 plus the 32.07 plus 16 times 4 for a total of 64. So if I add all those masses together, I'm going to grab my calculator really quickly. That gives us 174.27 grams per mole. And for our last example, I have 3 atoms of barium, and each atom of barium is 137.33. I'm going to add that now with the parentheses. Just like in math, with the coefficient out in front, we're going to distribute this. So I'm going to have 2 atoms of phosphorus, each one being 30.97, plus now 8 times 16. So when we do that, 137.33 times 3 plus 2 times 30.97 and 8 times 16, that gives us a grand total of 601.93 grams per mole. Okay, so now we're going to look at our mole conversions. So again, converting between mass, number of moles, and number of particles to begin with. So you always want to use the dimensional analysis method to figure this out. Write your units in your final answer, and make sure that as you're writing out, you're showing your work, you're listing both the unit and the substance for these problems. And then finally, determine the unit factors. Again, the 1 mole equals the molar mass, 6.02 times 10 to the 23rd. We'll get to the last one with the 22.4 liters as well. That'll be necessary to solve the problem. So this is where, again, where you want to incorporate your mole roadmap to figure these out. Okay, so we're going to start our set of practice problems. So again, here I'm starting with the number of grams of helium, and I'm trying to go to moles. So if you pause it and go back and look at your mole roadmap, you should hopefully see that we have a one-step problem. So I'm going to start off by writing 5 grams of helium. And when I make my little conversion, I need my molar mass. And again, I have those 2 options to choose from, but I'm going to take the one with the grams of helium in the denominator and moles of helium in the numerator. So 1 mole of helium would be 4.00 grams of helium off of your periodic table. And so I would have 1.25 moles of helium. So as we look at our second problem, how many moles of neon are in 250 grams of neon? I should have mentioned this before. Notice here with the 5.00, that has 3 significant figures. So my answer is rounded 1.25 to have 3 significant figures. 250 with the decimal point, that has 3 significant figures. So I'm going to round my answer to 3 significant figures. So I would have 250 grams of neon. And once again, I need grams to be in the denominator. 1 mole of neon in the numerator. For all your conversions, it will always just be 1 mole. And then off of your periodic table, you should notice the molar mass of neon is 20.18 grams. And so now I can plug in my values, and we end up with 12.4 moles of neon. And our last example, so this next one we have now to calculate how many neon atoms are present. So for this, again, we're going to now have a two-step process. I need to take it from grams to moles, just like we did in that last problem, or last two problems, and then we're going to do one extra step and convert from moles into atoms. So for this, I can take 2.0 times 10 to the third grams of neon. Notice I have two significant figures, so I'm going to take that and divide it by the 20.18 grams of neon found in 1 mole. And now I'm going to add one last step, which will be 1 mole of neon, now to get the moles to cancel, and then 6.02 times 10 to the 23rd atoms of neon. So when I type that in, that gives us an answer of 6.0 times 10 to the 25th atoms of neon. Two significant figures. So the next three, I want you guys to pause the video and try yourself. And now we're going to go through the answers. So we have, in this first example, 50.0 grams of water. So for this compound, again, I need to find its molar mass. So I have the 50 grams. Again, I need the grams to cancel. So off of my periodic table, I have 2 atoms of hydrogen, each one 1.01 plus 16. So I know that 1 mole of water will be the equivalent of 18.02 grams of water. And now I can solve, and that will be 2.77 moles of water. In my second example, I have how many N2O molecules, dinitrogen monoxide, are present in 150 grams of dinitrogen monoxide. So in this case, I have a two-step problem once again, looking at your roadmap. So I'm going to go first from the mass to the moles, so using the molar mass. So I have 150.0 grams of N2O. So notice now I have 4 significant figures. So I'm going to make my little T-chart. 1 mole of the N2O, notice again symbol and substance. And the molar mass of that, 2 times 14.01, 28.02, plus 16. So I have a total of 44.02 grams of N2O. And for my last step, because it's asking us for molecules, I can now say that 1 mole of N2O is the equivalent of 6.02 times 10 to the 23rd. Remember, you can abbreviate molecules as MCs for me, of N2O, and solve. And when we do that with 4 significant figures, we have 2.051 times 10 to the 24th molecules of N2O. And for my last example, how many Cl atoms are there in 100 grams of Cl2? So this one is similar to the silicon tetrafluoride question that we did earlier. Because the chlorine atoms are part of a compound, we're going to first go to molecules and then multiply by the number of molecules found in, number of atoms found in one molecule, excuse me. So we have 100.0 grams of Cl2. First step, getting rid of the mass and converting it into moles. So I have 1 mole of Cl2 in the numerator. I have 2 times 35.45, which is 70.90 for my grams of Cl2. To now get rid of my moles, I'll have the moles in the denominator, and I'll have 6.02 times 10 to the 23rd molecules of chlorine. And then for my last step, for every 1 molecule of chlorine, I have 2 atoms of chlorine. And now I'm ready to solve. So for significant figures, once more, I would have 1.698 times 10 to the 24th atoms of chlorine. So the last of the mole conversions that I'm going to show you in this video is for molar volume. And this is the volume that is occupied by 1 mole of any gas. So at the beginning we talked about Avogadro's law that he came up with, and he basically said that at the same temperature and pressure, equal volumes of gases will contain the same number of molecules. So it is irrelevant what the identity is for the substance. 1 mole of a gas at STP will always equal 22.4 liters. Again, STP stands for standard temperature and pressure, 0 degrees Celsius, 1 atmosphere. So for the 2 conversions, I have either 1 mole over 22.4 liters. Again, I'd use this when I'm starting with liters, trying to convert it into moles. Or if I'm trying to go from moles into liters, I'd have 22.4 liters over 1 mole. So now let's look at some practice problems. Okay, so we're now going to look at a few example problems here. The first one we're going to look at is what mass of CO2 occupies a volume of 25 liters at STP. So for this first problem, we're going to start with volume, and I need to convert it into moles. So I'm going to take my 25.0 liters of CO2 and convert that into moles. So 22.4 liters of CO2 will occupy, or be 1 mole of CO2, and we'll then go from 1 mole of CO2 into mass. So for the mass, I need to determine carbon dioxide's molar mass. I have 12.01 for carbon plus 2 times 16 for oxygen. So I'd have a total of 44.01 grams of CO2. When I multiply and divide, that will give me a total of 49.1 grams of CO2 with 3 significant figures. For the second problem, I have 10 grams of propane gas. Again, that is what you use in your gas grills outside, more than likely. We have 10 grams of propane gas at STP, and it's looking for the volume. So the first step I need to do is convert from mass into moles. So I'm going to use my molar mass. So 10.0 grams C3H8. The molar mass for propane would be 44.11 grams. Again, 3 times 12.01 plus 8 times 1.01 to give us a grand total of 44.11. And that will get my grams to cancel. I need to get my moles to cancel. So 1 mole of the C3H8 will be 22.4 liters of propane. And now when I plug that in, we need 3 significant figures. So I'd have 5.08 liters of propane. And now for my last problem. We have how many molecules of dinitrogen tetroxide, that's N2O4, are present in 35 liters at STP. So I'm going to begin with the 35.0 liters, 3 significant figures again, N2O4. I need to convert that into moles. So 1 mole of the N2O4 will be 22.4 liters. And then our last step in this process, because we're trying to go to molecules, we don't have to deal with mass. So I could have 1 mole of the N2O4 will be the equivalent of 6.02 times 10 to the 23rd molecules of N2O4. And if we plug that into the calculator, we end up with 9.41 times 10 to the 23rd molecules of N2O4. We're now going to begin the application phase of the mole concept. The first application that we're going to do for the mole is percent composition of compounds. You'll also see this termed as mass percent composition or just a mass percent. And for the mass percent concept, we're going to find the mass of each individual element that's present in a compound by dividing the mass of the element by the total mass of the compound. There's a couple of easy steps that you're going to do. There's a number of different ways that it can be done for these types of problems, so we'll look at those. But the typical steps that you're going to have, you need to calculate the total mass of each individual element in the compound, and then add up all the masses of each element to get the total mass, or the molar mass, for the compound, and then simply divide the mass of each individual element with the molar mass of the compound. The first example problem asks us to determine the percent composition by mass of each element present in hydrogen peroxide. So the first thing we need to do is to determine the molar mass. Now I like to try to keep things very organized here, so hopefully that'll kind of help you in determining the molar mass, which will also help you set up the problem. I'm just going to simply take my number of atoms and then the mass from the periodic table to give me the total mass. You don't have to do this on every problem. It just gives people a way to kind of stay organized. So for the hydrogen, I have my number of atoms, 2, mass from the periodic table, that's the PT that's here, 1.01 grams per mole. So that will give me a total mass of 2.02 grams. When I look at oxygen, I have 2 atoms as well. Mass from the periodic table, 16.00. So that will give me 32.00 grams coming from the oxygen. So if I add those together, that gives me a grand total of 34.02 grams per mole. So as I now come and look at my percentages, for the percentage of hydrogen, all I have to do is take my total mass from here, 2.02 grams, divide it by the molar mass, 34.02 grams per mole, and finally, since we're dealing with a percentage, multiply it by 100%. For your answer, you can just, in these types of problems, because if you notice there are no numbers given, so we can't really have any sig figs, so just round to the hundredths place. So for this first one, we would have 5.94%. Now, I realize because we're dealing with percentages, everything adds up to equal 100. So I should just be able to take the 5.94 and subtract to solve for the percentage of oxygen. But let's just go through it for practice and make sure that you understand where it's coming from. So I would have 32.00 for my grams of oxygen, and I'm going to divide that by the molar mass, 34.02 grams per mole, and again multiply it by 100%, and we come up with 94.1% or 0.06%. So as you guys are doing this, don't be concerned if just with the rounding, especially when you get more than 2 elements present in a compound, you may have all of your percentages just due to the rounding add up to equal 100.1 or 99.9. That's okay, you're not doing anything wrong, it's just the limitations of what we're rounding with. So we're now going to look at our second problem. So for this one here, again I have to determine my molar mass for the silver sulfate compound. So I have 107.87 for silver, and we're going to multiply that times 2, and that will give us, do my little chart here again, number of atoms, our mass from the periodic table, and finally our total mass for the compound. So for silver, again I have 2 atoms, 107.87 grams, so that'll give us a total mass of 215.74. For sulfur, I have 1 atom, 32.07 grams, So I'd have 32.07 grams for sulfur. And finally, oxygen, I have 4 atoms, 16 grams. So I have a total of 64.00 grams for oxygen. So if I add all those together to determine my molar mass, that gives us 311.81 grams per mole. So in this case, notice here we're finding the mass of each element percentage-wise. So for silver, I'd have 215.74 divided by the 311.81 for our grams per mole, multiply by 100%, and we will have 69.19% silver. For sulfur, I would take 32.07 for our grams of sulfur and divide that by the 311.81 for our grams per mole of the compound. Again, multiply by 100%. And that will give us 10.29%. And finally, for our percentage of oxygen, we have 64 divided by 311.81, multiplied by 100%, and that will give us 20.53% for oxygen. So there's our answer. 3 parts for those. Okay, so for example 3, please stop the video and try to work the problem out for yourself before we try a new problem in 4 and 5. So as we look at question number 3, we have what is the percent composition by mass of each element in aluminum carbonate? Al2CO3 parentheses 3. So same type of thing. I start off, get my molar mass for all these, number of atoms, the mass from periodic table, and the total mass. So like I said, you don't have to do this. If it helps, great. I'm just trying to be really organized for you. So I have 2 atoms. The mass of aluminum off the periodic table, 26.98 grams per mole. And so that is going to give us a total mass of 53.96 grams. For carbon, I have 3 times 1 for a total of 3 atoms, each one being 12.01 for the molar mass. So that there will give me a total mass of 36.03 grams per mole. And then finally for oxygen, I have 9 atoms, again 16.00 grams per mole. So I have 144 grams per mole for oxygen. So if I add all those together, 144 plus 36.03 plus 53.96, that gives us 233.99 grams per mole. So to find the percentage of aluminum, I'm going to take the 53.96 grams, divide it by 233.96, multiply it by 100%, and that will give us approximately 23.06%. When I look at the percentage of carbon, 36.03 divided by 233.99 and multiply it by 100%. So 36.03 divided by 233.99, that gives us 15.40 for my percentage of carbon. And my last one, percentage of oxygen, 144 divided by the 233.99 multiplied by 100%. And we end up with 61.54% oxygen. Okay, so in our next example, now we're looking to solve for just the mass of magnesium that are found in 50 grams of magnesium chloride. So this is the key thing for you. With this type of problem, because I'm looking for just magnesium, I can find the percent composition of magnesium in the magnesium chloride compound, and then instead of just multiplying it by 100, I can multiply it by the 50 grams. Now, if we do this from a dimensional analysis standpoint, I can simply do this, where I have the grams of magnesium over my grams of magnesium chloride. Hopefully you can kind of see this mimics what we were doing up here in these problems by taking the mass of the element divided by the mass of the compound. So if I look at the mass of magnesium off the periodic table, I'd see 24.31. And then for the magnesium chloride, I'd have 24.31 plus the 70.9, or 2 times 35.45. And when I would do that, I would get 95.21 grams. Now, I can use this as a conversion factor, but I'll do it both ways just so you can kind of see. So if I start from a percent magnesium standpoint, I could then take that number, 24.31, divide it by 95.21, multiply by 100%, and I would get 25.53% magnesium. I could then take this percentage and multiply that by 100%. I could then take the 50.0 grams of the magnesium chloride and multiply it by that 25.53% magnesium. So remember, we divide that by 100 to get rid of the decimal. And when I multiply that by 50, it gives us, with 3 significant figures, 12.8 grams of magnesium. But like I said, there's a little bit easier way that we could do this. And so I'm going to do that one right underneath here. Let me just kind of draw a line out here so you can see a little bit more simplistic process. So I can take the 50 grams of the magnesium chloride, and hopefully you can kind of see here with my grams of magnesium chloride, I can place that into the denominator. And as I was mentioning here, if I do the molar mass, 95.21 grams of magnesium chloride, there are 24.31 grams of magnesium inside. So notice here, here's my percent composition concept right here that we're now just plugging into dimensional analysis type problems. So I can now get my grams of the magnesium chloride to cancel. I'm left with grams of magnesium in that process, and I can now solve. So when I would plug that in, this again here would be the 0.2553 for that percentage, and I can multiply by 50, and I'm still going to come up with 12.8 grams of magnesium. So you can do these problems either way, but again, the dimensional analysis version is just going to be a little bit faster for you to do. So your call whether you want to do it option 1 or option 2, but either way, it'll be a little bit easier for you if you do it the second method. So if we look at our second problem, calculate the mass of sulfur present in 125 grams of lithium sulfide. So same type of concept. I need to start off figuring out the molar mass. So I have 6.94 times 2 plus 32.07, and we have a molar mass equal to 45.95 grams per mole. So at this point, if I were to take 125 grams of the Li2S, I have my molar mass, 45.95 grams. and I have 32.07 for my grams of sulfur. So if I now take that, 125 divided by 45.95 and multiply it by 32.07, I end up with 87.2 grams of sulfur. Okay, so the last type of problem we're going to do for percent composition is a special application that we deal with in the lab, and that is finding the percent composition of a hydrate. So first we need to define a couple of terms. A hydrate is going to be an ionic compound that has water trapped inside of its crystals. The second vocabulary term that we need to talk about is something that we call an anhydrous salt. That term anhydrous means lacking water. So the anhydrous salt would literally be just the ionic compound without the water. So in this example where I have the Na2CO3, that would be the anhydrous salt, whereas the entire compound would be the hydrate. So for this type of problem, it follows the same exact concept. We need to determine the molar mass of the compound. So the molar mass for Na2CO3.H2O is 286.19 grams per mole. The amount of water that we have for the compound, 10 times the 18.02, will give us 180.2, and if we divide that by 186.19, multiply by 100%, and that will equal 62.97%. The second application of the mole concept that we're going to focus on is empirical and molecular formulas. To begin with, the empirical formula is the simplest whole number ratio of the atoms in a compound. The term empirical means simplest. So when we're talking about these types of problems, we are looking at lab data to try to determine the unknown compound that we're looking at. A molecular formula is simply going to be a chemical formula that is a whole number multiple of the empirical formula. Now, the empirical formula in many instances will be the same as the molecular formula, but it doesn't have to be. The molecular formula will always be a whole number multiple of the empirical formula. Now, from a conceptual standpoint, I just want you guys to understand that the empirical formula process is essentially the exact opposite of the percent composition. In percent composition, we have a known compound with a known chemical formula, and all we're trying to do is determine how much of each of the elements are present within that compound. For an empirical formula, because it's an unknown, we're taking the lab data and determining from the amounts of each element that are present in that compound what the chemical formula happens to be. So the first thing that I want to do is just give you some examples of how to look at something simple when we have the chemical formula and determine what the empirical formula would be for that. So in our first example for glucose, everybody's favorite molecule in biology, we have C6H12O6. So hopefully you can see with each of my numbers for these subscripts, I can divide by 6. Which would give me the simplest whole number ratio of CH2O for this particular compound. When I look at caffeine, I have C6H10N4O2. That is the chemical formula, molecular formula. Hopefully you notice with each of these numbers, they are divisible by 2. So I would have 3 carbons, 5 hydrogens, 2 nitrogens, and 1 oxygen. And for our last example, acrylonitrile, I have a molecular formula of C3H3N. In this compound, you'll notice I have a 3:3:1 ratio. So in this example, the empirical and the molecular formula are identical because I cannot reduce the nitrogen atoms any further. So the first thing that we need to do when we're trying to determine the empirical formula is we need to look at the lab data and find the number of moles of each element that are found in the compound. Once we have figured out our number of moles, we want to get a mole ratio, because if you remember, no matter what the substance is, I would be simply multiplying by 6.02 times 10 to the 23rd to get it into atoms. So if I find my smallest number of moles and divide each element by that number of moles, that's going to give me a ratio not only of the moles, but a ratio of the atoms as well. And so once I get that ratio, I need to just simply make sure that it is in a whole number ratio. If it's not, then I'm going to find a number that I can multiply everything by to make all of them whole numbers. So if I have a 0.5 involved in my ratio, whether it's 1.5, 2.5, 3.5, it'll never be 0.5 itself. I would multiply all of my subscripts by 2. If I have something like 0.33 or 0.66, I need to multiply all subscripts by 4. If I have something like 0.25 or 0.75, then I need to multiply all my subscripts by 4. Now, as you start to get down into your percentages or your ratios there, you need to be really careful, because if I have something that's 2/5, that's very close to 0.33. So we need to be very precise in our calculations to make sure that we know which thing we're multiplying it by. So my suggestion to you would be to make sure that you write your answers to at least 4 significant figures when you do this. That should take any ambiguity out, because if it's showing up on your calculator with 3 significant figures or 2 significant figures as 0.37, then it could be very easily go to 0.4, or it could go down to 0.33. By doing more numbers for that ratio, I might find that it goes from 0.37 down to 0.34, in which case I would know to multiply by 0.3 instead of, or to multiply by 3 instead of by 5. So I now want to work my way through one of the example problems. So I have 25 grams total of a compound of nickel oxide, and it's found to consist of 17.74 grams of nickel and 7.26 grams of oxygen. So again, my first step was to convert the grams into moles. So I'm going to start with 17.74 for my grams of nickel. Off of the periodic table, 1 mole of nickel is 58.69 grams. And so when I multiply that out, that gives me with 4 significant figures, 3023 moles of nickel. And when I look at oxygen, 7.26 grams of oxygen, 1 mole of oxygen atoms, 16.00 grams of oxygen. And now when I multiply that, or divide that, I have 0.4538 for my moles of oxygen. So I now have my 2 sets of moles, so I need to get my mole ratio. The easiest thing to do is to divide by the smallest number of moles. So I'm going to divide each one of these by the 0.3023 moles. And when I do that, obviously this would be a 1, and this would now be 1.50. Okay, so hopefully you can see now I need to keep this 1 to 1.5 ratio the same. So as I was talking about earlier, if I wanted to do this and multiply each by the 6.02 times 10 to the 23rd, it's completely unnecessary, but I have 6.02 times 10 to the 23rd here. If I multiply this by 6.02 times 10 to the 23rd, hopefully you can see I have the exact same multiplier for each of these numbers. So when I have 9.03 times 10 to the 23rd, I would go down and try to reduce this ratio, and I would still end up with the exact same thing, which would be a 2 to 3 ratio. So instead of doing all this, I can just simply look at my ratio of the moles to give me my number of atoms. So I'm going to take this and multiply it by 2. By doing so, I would have 2 atoms of nickel, and I would now have a whole number of 3 for my atoms of oxygen. I still have that ratio the same, 2 to 3 still is equal to 1 to 1.5, but I now have all whole numbers. So my final empirical formula for the nickel oxide compound would be Ni2O3. In example number 2, we're going to determine the empirical formula for ascorbic acid, which is also commonly known as vitamin C. It is a hydrocarbon derivative, a compound that consists of carbon, hydrogen, and oxygen. So in this particular process here, you can notice they gave me a total mass for the sample, and then they gave me just the grams of carbon and the grams of hydrogen. So in order to determine the empirical formula, we need to determine how many grams of oxygen we also have in this compound. So I'm going to take the 25.00 for my grams of the CH and O compound. I'm going to subtract off 10.23 for my grams of carbon and 1.14 for the grams of hydrogen to equal my grams of oxygen. So I know when I do this, my grams of oxygen will be 13.63 grams. So I now have my starting masses for each of my compounds, so I can begin the process. So I'm going to take the 10.23 for my grams of carbon, divide by its molar mass, so 1 mole of carbon, periodic table, 12.01 grams, and that equals 0.8518 moles of carbon. I have 1.14 for my grams of hydrogen, and when I do 1 mole of hydrogen, 1.01 grams, that is equal to 1.129 for my moles, and finally 13.63 for my grams of oxygen, 1 mole of oxygen, 16.00 grams, and I end up with 0.8519 for my moles of oxygen. So again, just due to some rounding issues with our measurements, we're not exact, but we're really close in that ballpark. So if I take and divide each one by 0.8518 for my number of moles with the smallest amount, when we divide this by 0.8518, you end up with 1.00008. So we're just going to call that 1 because it's again within a tenth. For this one here, 1.129 divided by 0.8518, that is equal to 1.325. So we'll just say 1.33. And then finally we would have 1 for this. So for this ratio here, again, I have 2 whole numbers, but that 0.33, I need to convert that into a whole number. So the easiest thing to do to get rid of that 1.33 is to multiply everything by 3. So that would give me, in this particular instance, C3 H4O3 for the empirical formula. So now we're going to look at the calculation to determine the molecular formula. The molecular formula for the compound is, again, some whole number multiple of the empirical formula. You should never get a fraction involved in this process. It should always be a whole number. So for the molecular formula, you'll typically be given the molar mass of the compound, and you will need to calculate the molar mass of the empirical formula. Simply divide the molar mass of the compound by the molar mass of the empirical formula, and that will tell you some factor n to which you will multiply each subscript in that empirical formula. So again, you can take the molecular formula mass, divide it by the empirical formula mass, and that'll equal some number n. And then from there, we can take whatever the empirical formula is and multiply it by that value for N and distribute it to your subscripts. So if you think about the example we just got done working for ascorbic acid, we had an empirical formula that was equal to C3H4O3. So now let's figure out the empirical formula's molar mass. So when I do that, I have 3 times the 12.01 plus 4 times 1.01 plus 3 times 16, and that gives us a grand total of 88.07 grams per mole. In the problem, they gave us 176.1 grams per mole for the molecular formula for the compound. So now I can take that molecular formula mass, divide it by the empirical formula's mass, and that'll equal some number N that we're going to multiply everything by. So I would take the 176.1 divided by the 88.07, and that would equal 2. So for my molecular formula, that would be equal to C3H4O3, having that 2 distributed. So I'd have C6H8O6 for the molecular formula. Now we're going to look at the type of problem where instead of giving you lab data where you have the number of grams of each compound that are present, they're going to give you some type of analysis of that lab data and give you percentages of each element that are present in the compound. It's a very similar process. The only thing that we have to do is just convert those percentages into grams. And since we're dealing with percentages, the easiest thing to do is to just arbitrarily assume that we have 100 grams of the compound. That way, whatever your percentage is for each element, you can simply take that and multiply by the 100 grams, and that'll tell you your number of grams for the compound. So if I look at this example problem here, once I have done that, I can follow the same exact steps that we've done previously. But I could just, as an example, if I say that I have that 100 grams of the compound, and I know that 74% of it is carbon, I could just make the assumption that 100 grams times the 74.03% carbon would give me 74.03 grams of carbon. And that way you can literally just take and change those percentage signs into grams for each of these different substances. Now I'm going to work this problem out this way to begin with, and then I'm going to show you a little shortcut method that you can do only for the molecular formula problems. But you need to, because a lot of times you're just going to be asked to find the empirical formula and not the molecular formula, so you need to understand the empirical formula process. So I'm going to begin by solving for the empirical formula for quinine, which is an anti-malarial drug. It is a compound that consists of 74.03% carbon, 7.47% hydrogen, 8.64% nitrogen, and 9.86% oxygen. If quinine has a molar mass of 325 grams per mole, determine the empirical and molecular formulas. So the first step that I would do is convert each of these into moles. So 1 mole of carbon, 12.01 grams. And when we do that, we end up with 6.164 moles of carbon. We have 7.47 for my grams of hydrogen, and we need to convert that into moles as well. So 1.01 grams of hydrogen, and that will give us 7.396 for our moles of hydrogen. We have 8.64 grams of nitrogen. So 1 mole of nitrogen, 14.01 grams, and that will give us 0.6167 for our number of moles of nitrogen. And then lastly, we have 9.86 for our grams of oxygen. 1 mole of oxygen, 16.00 grams. And that will equal 0.6163 for the moles of oxygen. So I now have my number of moles for each element. So again, divide by the smallest number of moles. That would be the 0.6163. Sorry, my computer is lagging there and not allowing me to see my cursor. So for this one, obviously it's a 1. This one is close enough since we're talking about a difference of 4/10,000ths. So that is going to be a 1 for the nitrogen. For my hydrogen, 7.396 divided by 0.6163. That's going to equal 12.0006. So we have 12. And then the carbon, 6.164 divided by 0.6163. That's going to equal 10. So my empirical formula will simply be C10H12NO. So molar mass for this one, if we did that, we'd have 10 times 12.01 plus 12 times 1.01 plus 14.01 plus 16.00, and that gives us a molar mass of 162.23 grams per mole. It gave us a rounded molar mass to 325. So if I want to figure out the molecular formula, again, since that's 325, I can now take that and divide it by the 162.25 or 23, and that's going to equal 2. So my molecular formula will be C10H12NO times 2, which would be C20H24 N2 and O2. Okay, so I'd have that final answer. Okay, now as far as that little shortcut method is concerned, what you could do is just simply take the molar mass. So I could take 325 grams per mole, and I'm just going to do this for one or two of the elements so you can see how it matches up, and I'm going to multiply that times the percentage of the carbon. And if I take 325 and I multiply it by 0.7403, again dividing by 100 to get rid of the percent, that would tell me that out of that 325 grams per mole, 240.6 of those grams are carbon. And so if I take the 240.6 and I divide that by the molar mass of carbon, if I divide by 12.01, you'll see that it comes out to be 20.03. So that would tell me again, this would be my number of atoms of carbon. Notice here I've got 20. For my final answer, I have 20. If I would do the same thing for, say, oxygen, if I do 325 for my grams per mole, and I multiply that times 9.86 for the percentage of oxygen, 325 times 0.0986, that would tell us that we had 32.045 grams of oxygen. If I now divide that by 16 for my grams of oxygen per mole, that would give me 2 for my number of oxygen atoms. So again, 2.003. So hopefully you can see here, this number matches with this number. So you can simply take the percentages. If it's asking you only to solve for a molecular formula, multiply the percentage of each element by the molar mass of the compound. That'll tell you the total mass for the element, and then divide by its molar mass to get it into atoms. Either way, again, let me just cut this off as like the little shortcut method here. Either way, you can solve the problem, but this way, if it's just a molecular formula like on a multiple choice question, this would be the easier format to use to solve for it. Okay, so the last type of problem we're going to do for empirical formulas is to determine the formula for a hydrate. So in this type of laboratory procedure, we're trying to find an unknown compound's amount of water. So in this lab process, we essentially evaporate the water out, just heat the substance up until we get rid of all the water. Typically, you can see something like a color change for the crystals to let you know when that happens. But in this example, we're going to take a 20-gram sample of the unknown hydrate of magnesium sulfate, MgSO4.NH2O, and it was analyzed in the lab. After heating the sample, it was determined that 9.766 grams of the anhydrous salt remained. Determine the value for N for the compound. So for this, we need to first determine how much water was present in the compound. So I'm going to take my total mass of the sample, 20.00. I'm going to subtract off the 0.9766 grams, and that would be for the MgSO4. And that'll tell me how much we have for the water, which in this case would be 10.234 grams. So now it is easiest to treat this problem like an empirical formula problem. Instead of doing each individual element, we can compare the mass of the anhydrous salt to the mass of the hydrate. So I'm going to start by taking 9.766 for my grams of magnesium sulfate, and I'm going to convert that into moles. So 1 mole of magnesium sulfate will be 120.38 grams. And then I'm also going to take 10.234 for my grams of water and convert that into moles as well. So 1 mole of water will be 18.02 grams. So when we get our total number of moles for the magnesium sulfate, we end up with 0.0811 moles, and for the water we end up with 0.568 moles. So if I now take each of these and divide them by 0.0811, we end up with 1 for the magnesium sulfate, and then we end up 7.002, so we can just call that a nice even 7. So I know then that my value for N will equal 7. So the formula for my hydrate, I'd have MgSO4.7H2O. So we would call this magnesium sulfate heptahydrate, with the hepta meaning 7. Okay, so now we're going to get into the most complicated form of these problems, and that is when we talk about a combustion analysis. So please understand, for a combustion analysis, this is a process that is used in the lab to determine the chemical formula for an unknown sample by taking a weighed sample of the compound and either decomposing it or reacting it with oxygen to produce new substances such as carbon dioxide, water, or something like nitrogen gas, which are then collected and weighed. To find the empirical formula for the hydrocarbon, we're going to use a two-step process. The first thing, because we're now going to be given information about the compounds that are formed, we're going to convert the mass of carbon dioxide to just the mass of carbon by using percent composition. So this is just going to take one extra step. We're going to do the percent composition first to determine what mass of the carbon or the hydrogen, typically, because they typically are looking at hydrocarbons for this. And then from that information, we'll be able to then use our normal steps for empirical formulas and solve the problems. Okay, so you do the same thing, use a percent composition for hydrogen found in water, and then from that you could determine the number of grams of hydrogen that are found in that hydrocarbon. And then lastly, if there's a third element, then you could take the total mass of the sample, subtract the mass of the carbon, subtract the mass of the hydrogen, and then you're left with the other mass for the other element. If it's just carbon and hydrogen, you should be able to just simply add the two masses together and it should equal the mass of the compound that was given in the problem. And then from there, just convert those using your empirical formula concept to solve the problem. So I know that's kind of a lot here. I'm going to show you guys the device of basically how this works on the next slide, and then we'll work on some practice problems. So here's our illustration of the device that will be used during a combustion analysis. So we have a furnace which is going to allow the hydrocarbon to be combusted. It's going to have O2 that's going to be pumped into the sample and allow it to burn. When that hydrocarbon burns, it is going to then create carbon dioxide, water, vapor, and other gases that could potentially be there. And as it passes through these next two chambers, they're unique to react with specific gases. So the magnesium perchlorate that is found in this first chamber, that is a substance that will be absorbing water. So any water vapor that passes through this chamber would then react with the magnesium perchlorate and would be absorbed. So they can take a measurement of the before and the after mass of the chamber 1, and that will tell how much water was released during the combustion process. In the second chamber, it has sodium hydroxide found in it, NaOH, and this will be something that will absorb carbon dioxide. So as the CO2 is passed through this second chamber, it will then be absorbed by the sodium hydroxide. They can measure the differences in masses of those two compounds, and that will tell us the mass of the CO2 that was absorbed. And then finally, any other gases that could be found in the mix will just be pumped out through that last end of the chamber. Now, that's not a big deal. If this has a 3-element compound in that sample, then by knowing the mass of the CO2 and the mass of the H2O, we can then work backwards and find the mass of the third element by just simply subtracting. So in this first example, we have a sample of fructose, 3 grams, which contains carbon, hydrogen, and oxygen, underwent combustion analysis to produce 4.40 grams of carbon dioxide and 1.8 grams of water. Determine the empirical formula for fructose. So the first thing that we need to do is convert from our mass of carbon dioxide into mass of carbon. So for that step 1, I want to take the mass of carbon divided by the mass of carbon dioxide and multiply it by the given mass of CO2. So I take the 4.40 grams of CO2, and then I'm going to multiply that 12.01 for my grams of carbon, 44.01 for my grams of CO2. When I multiply and divide those out, I should get 1.20 for my grams of carbon. Next, for the hydrogen, I want to take the mass of the hydrogen divided by the mass of the water, and I'm going to multiply that times the mass of the water. That will give me the mass of the hydrogen. So I have 1.800 grams of the water. For every 18.02 grams of water, we have 2.02 grams of hydrogen. Remember, in this case, it's because we have 2 atoms of the hydrogen there per molecule. So as I look at this one now, 1.8 divided by 18.02 times 2.02, that gives us 0.2018 for our grams of hydrogen. So for this sample, I can now take these two amounts and subtract them off to give me the mass of oxygen that was present in the compound. So since I have 3.00 grams, I can subtract 1.20 and subtract 0.2018. And when we do that, that gives us 1.598 for my grams of oxygen. So now at this point, I have a mass of hydrogen, a mass of carbon, and a mass of oxygen. So I'm ready to do my empirical formula problem. So like I said, it's one extra step where I'm doing the percent composition first of the carbon dioxide in the water to get the mass of carbon and the mass of hydrogen. And now I have just a simple empirical formula problem. So I have 1.20 for my grams of carbon, and 1 mole of carbon, 12.01 grams of carbon. So hopefully you can see that will give me 0.100 moles approximately. If we do the exact number, it gives me 0.09992 for that. So this should be close enough. When I look at the hydrogen, 0.2018 for my grams of hydrogen. Again, 1 mole of hydrogen. Now we're just talking about an atom, so I'm going to go back to 1.01 instead of the molecule's mass. And if I do that, 0.2018 divided by 1.01, that gives us essentially 0.1998 or 0.200 for my moles of hydrogen. And lastly, for the oxygen, we have 1.598 for my grams of oxygen, and when we divide that by oxygen's molar mass, that will also give us approximately 0.100 moles. So now, if you look at my ratio, if I divide each of these by 0.100, I'm going to have a 1 to 2 to 1 ratio. So my empirical formula would be CH2O. For our second example, we have a compound with a known molecular weight of 146.99 grams per mole that consists only of carbon, hydrogen, and chlorine, was studied by combustion analysis. A 0.367 gram sample was combusted, 0.659 grams of CO2, and 0.0892 grams of water formed. What are the empirical and molecular formulas? So again, to start off this problem, because I have 3 elements present, I need to figure out the mass of carbon and hydrogen and then subtract it from the initial amount to get the mass of chlorine. So let's start with that. So for our mass of carbon, we're going to take the 0.659 grams of CO2, and we're going to convert that into the grams of carbon by multiplying by 12.01 and dividing by 44.01 for our grams of CO2. And when we do that, we end up with 0.1798 grams of carbon. For the grams of hydrogen, we're going to take the 0.0892 for my grams of water, and we're going to multiply that by the 2.02 for my grams of hydrogen divided by the 18.02 for my grams of water. And when we do that, we end up with 0.009999 for my grams of hydrogen. So to solve for my grams of chlorine, I'm going to take the 0.367 grams of the CH and Cl compound, and then I'm going to subtract the 0.1798 and the 0.009999 for my 3 grams. And when we do that, we end up with 0.1772 for our grams of chlorine. So I now have my starting masses. So I can take the 0.1798 for my grams of carbon and convert that into moles. So 1 mole of carbon, again 12.01 for my grams of carbon. And if we do that, we end up with 0.0150 for our moles of carbon. We take 0.009999 for our grams of hydrogen, and again we're dividing this by the 1.01 since we're talking about atoms of hydrogen. And we end up with 0.00999 for that. And then finally for the chlorine, we can take the 0.1772 for my grams of chlorine. 1 mole of chlorine is going to be 35.45. And that gives us 0.005 moles of chlorine. So now finding this, I have 0.00500, 0.00500, and 0.00500. So now when I do this, I end up with 3 atoms of carbon, 2 atoms of hydrogen, and 1 atom of chlorine. So my empirical formula would be C3H2Cl. And now from there, the molar mass of this compound, we would have 3 times 12.01 plus 2 times 1.01 plus 35.45, and that gives us an empirical formula mass of 73.5. So now if I take the molecular formula mass divided by the empirical formula mass, that'll tell me N. So I have 147 approximately, and that 146.99 divided by 73.5, so that equals 2. So my molecular formula would be C6H4Cl2. Okay, so we have one last problem to go, and this says after combustion with excess oxygen, a 12.501 gram sample of a petroleum compound produced 38.196 grams of carbon dioxide and 18.752 grams of water. A previous analysis determined that the compound does not contain oxygen. Establish the empirical formula for the compound. So the significance of this statement is the fact that now I know this compound will contain only carbon and hydrogen. So to begin this process, I want to determine my grams of carbon. So I'm going to take the 38.196 grams of CO2 and I'm going to multiply it by 12.01 and divide it by 44.01 grams. So typing that into our calculator, we have 10.423 for our grams of carbon. For my grams of hydrogen, we have 18.752 for the grams of water. And we're going to multiply by 2.02, divide by 18.02 for my grams of water, and that gives us 2.10. So there's our grams of hydrogen as well. So at this point, if you were to take these two numbers and add them together, you will see that we come approximately to the 12.501. Again, we're off a little bit on our rounding just because molar masses are a little bit more exact than rounding to the hundredths place. But we're within that general ballpark here, 12.52 versus 12.501, so we're all set. So at this point, we can now take our amount of carbon. So I can take the 10.423 from my grams of carbon, divide 1 mole of carbon, 12.01 grams, and that leaves us with 0.8679 for our moles of carbon. And then we're going to do the same thing with hydrogen, 2.102 for my grams of hydrogen, 1 mole equals 1.01 grams, and I'm left with 2.081 moles of hydrogen. Excuse me. So 0.8679 is my smallest number of moles. Just going to divide each of these by that amount. And when we do that, I get 1 for the carbon and 2.4 for my number of hydrogens. So to make this correct, again, 1 carbon, 2.4. With that 2.4, I want to multiply each of these by 5. So that would give me C5 and then H12 for my final answer.